Hello everyone. So congratulations, first of all, you made it. This is the last class of physics, and on Wednesday we will take the exam. And again, there are no final exams because we will already have total of 7 exams, and that's more than enough. So I would like to go over some of the things on the equation sheet first, and I want to highlight a few things. I'm going to use the original form of the equation sheet, and I'm going to cross out the things that we didn't cover. Also, I want to highlight a few things about chapter 10 and 11. And not all the equations are at the bottom, so I want you to see the full picture. I also added some real cool demo videos to the video clips that I have for the class. We were going to do some of the demonstrations in the videos, but they're also like really cool explanations of angular momentum and also like torque and such. So please check those videos and have fun with them. Okay, so this is the equation sheet, and you're gonna get this one on the exam on Wednesday. So a couple things to highlight. First of all, the cross product is right on the first page, okay, and right here. So there are two equations, looks like it, right? The top one coming from the determinant. You don't need to memorize, like if you remember it when we discussed it, it was like fish to the right, fish to the left, and right again. And we did the determinant and find out the components of x and y and z for the resultant vector coming out of that cross product. Okay, so you use the first one here. You use this first equation here if the vectors a and b are given in terms of unit vectors. And all you need to do is, okay, vector a is given in unit vector. So when I find a cross b, I'm gonna look at the y component first because it says ay, and then find the z component of b and then put it in there. You need to include the signs, but you're not including I, j, or k hats, okay? Because you can see that I, j, and k hat are already here. Okay, we're just gonna multiply those. So the parentheses are basically the coefficients of I, j, k, so they are the components of your resultant vector. So you use this one if the vectors are given in unit vectors. Okay, I usually don't use this because this is more algebra, as you can see. I look at the problem, and if I know the magnitude of A and magnitude of the B, and I can see the angle between them, or I'm looking for something about this, but I can see most of those, then instead I use the AB sine theta, and that's equal to A cross B in magnitude. And the direction, I use right hand rule to figure out the direction. Okay, and majority of the time, this is what we use. But I want you to be aware there are two forms and they are the same thing. Okay, but you just need to choose the best way and the easiest way to solve. And it's so clear. If the vectors are given in unit vectors notation, use the top one. If the vectors are given in magnitude and the angle is given, or maybe you're trying to find it or something, then use the bottom one. Okay, but when you use the bottom one, as you can see, there's no ijk. That's just the magnitude, and you're going to find the direction using the right hand rule. So that's one of the equations. Another thing is, these are from like chapter 3, dot product and then cross product, and then the forces are from chapter 5 and 6. We still kind of use this equation too. If you recall this comes from the circular motion, right? And this is the centripetal acceleration for uniform circular motion. There's only radial acceleration, and that radial acceleration is defined as v squared over r. V is the tangential speed of the object going through a circular motion, and r is the radius. So you can also find the period, right? Using period is the specific time for the one cycle. So you just write out what is the distance for one cycle, which is the circumference of the circle, which is 2 pi r, and divide by that tangential speed again. Okay, and as you can see, we have that velocity tangential velocity being equal to angular velocity times r, given here as well. Okay, so those are still important. And now we are using our full equation in this form. Okay, so what we have is we have two kinetic energy terms, two potential energy terms, and two internal energy terms, and work done and the heat transfer on the right side. So most of the time, okay, these two are going to be zero in our class. The reason is we don't really have temperature pressure changes, molecular level changes in most of the problems, and heat transfer either. Sometimes we have friction, but it has to be kinetic friction. So it's right here. Kinetic friction doing the work. Static friction cannot do work, right? Because there's no displacement. It's static. So this is only the case when you have kinetic friction, then you will use that in here. And then you are going to ignore the work done by the kinetic friction, which will be this, right? Because you're using it in terms of delta IF, okay? The internal energy, or it's also called thermal energy, due to kinetic friction, okay? And again, if you don't have a spring, you're going to get rid of delta UE. If there's no change in elevation, you're going to get rid of delta UG. And if the object doesn't change its tangential velocity, then you're going to get rid of delta KT. And if the object doesn't rotate or doesn't have a mass, as we've been doing that initially, we had pulleys, but they didn't have mass. They were ideal. So we didn't worry about the rotational kinetic energy. So you gotta check if the pulley has a mass. If it doesn't say it's massless, don't assume it is massless. Okay, so you gotta be careful with your assumptions, because these chapters that we are covering, the last ones, are about rotation. So you will probably have this term in it. What is that term? Right here. This is the rotational kinetic term, right? 1/2. Moment of inertia is I, and angular velocity is omega. And the next one is translational kinetic energy. It is 1/2 mv squared, so the mass of the object and the tangential velocity of the object. It depends on those are the things that depend on kinetic energy. Okay, or actually kinetic energy depends on them. And yeah, so you already know like the potential energies that we discussed earlier. We still have the work done. If it's constant, we use that. If it is variable, we need to integrate it, right? Because we're still using the energy conservation, so be careful with that as well. And so for this case, since it's fd.dr, dr means there are three components, x, y, and z. From the dot product, this is what you really get. But as you can see, the result is not a vector because it's a dot product, it's scalar. And specifically, we did this for spring force, and this is what we got earlier, right? And we did solve some problems about that too. At the bottom, we have power. Again, that was the definition of power. Work divided by time, or energy divided by time. So it's joules per time or per seconds. We call the unit as watts. If the force applied is constant, then you can also find it as F dot V or FV cosine theta. And I'm going to talk about more in the next video.